This is a short addendum to my previous video about implementing a game of guess a number with the chemical machine. This was the final code that we ended up with in the previous tutorial, and it works, but I can run it. There's, however, some issue with this code which makes it less than perfect, and I will show you that essentially we need to optimize a little and dive a little deeper into the chemical machine in order to understand what is wrong with this code. So let me play the game. I'm pressing enter. I'm pressing enter. I'm pressing enter. I'm pressing enter. I'm pressing enter, and nothing. There is no prompt. My prompt came late. And the reason it came late, I'm going to stop the game now. This is actually arguably a bug. I can ask 4 questions, but no more than 4. After asking 4 questions, my prompt is delayed until an answer comes. And the reason is that my computer has only 4 cores, and only 4 concurrent computations of the answer run at the same time. So just to remind you about this implementation, the player asks a question, whether the answer comes in 10 seconds or 20 seconds, that's random. So this random delay simulates a computation that is necessary in order to compute the answer. And as we ask questions, the question molecule is emitted, and this molecule starts a reaction that executes a delay and then computes the answer. Now, if I ask 4 questions, then 4 of these molecules will be emitted, and 4 of these reactions are going on at the same time. If I now want to ask another question, this reaction needs to start. But this reaction cannot start because my thread pool only has 4 threads, and they're all busy. Now, until this point in the tutorial, we never thought about thread pools and how many threads there are. We treat the computer as if it has infinitely many threads, but this is not true. And in fact, we see that the program does not work correctly because of thread starvation. So this is actually a matter where you cannot just pretend that your computer has infinitely many threads, because you have here an actual bug, let's say. Your game doesn't work. You can ask only 4 questions at once, and when you want to ask a 5th question, you don't even get a prompt to ask it until an answer comes back, and then you get a prompt. So, and as we have seen, that screws up the user experience in this game. That makes the user experience incorrect. So let's analyze this code and see how we can resolve this. Well, one thing I can notice about this code is that the molecule idle gives rise to this reaction and is never consumed anywhere else. And this reaction doesn't have to proceed in parallel with the previous one, and it cannot actually. The previous reaction must be finished before the next reaction can start, and also can ask is only emitted at the end of this reaction, and so these two reactions never run in parallel. They cannot possibly run in parallel. Whereas this reaction can and will run in parallel with everybody else. Now the answer and can show cannot run in parallel with this either. It can run in parallel with this, though. Finally, this reaction will be run only once, but it could run in parallel with other reactions. Because game over could be emitted over here while one of these reactions is running. So the result is that we can run one of these two reactions in parallel with this one or in parallel with this one. Since we emit game over, we don't emit answer in that case. Well, but some other answer could be already emitted, and it should be shown. So this analysis tells us that basically this reaction has high parallelism. Many instances of this reaction could be running at the same time, but all other reactions have very low parallelism requirement. We could run fine with parallelism of 2 for all the other reactions combined. So the way to fix this problem with thread starvation is to separate these reactions into different reaction sites according to the required parallelism. So we see that this reaction requires a lot of parallelism, but the other ones don't. Also, this reaction has the only input molecule, which is question. No other reaction has that as input molecule, which means that this reaction could easily be separated into a different reaction site, and all the other reactions could remain in this big reaction site. At the same time, we need more parallelism for this reaction, but we don't need much parallelism for these other reactions. We need the parallelism of all the possible cores for this one, but we need maybe at most parallelism of 2 for all the other ones, because at most 2 of them will run at once. And finally, we could inline this reaction into this place. Instead of emitting idle, which will immediately start another reaction and do this, we can just put these molecules or function calls right here instead of emitting idle. So that would be simplifying the code, but not really changing the semantics of the game. So this is what I did in the next implementation. So now I have 2 reaction sites, and they need to be running on separate thread pools. If I want to fix the problem with my implementation, in the chemist library, the call to site activates reactions, and it needs to know what thread pool to run them on. By default, there is a thread pool that maximizes CPU usage. This is similar to Scala's default executor in this implicit global executor that we are familiar with when we're using Scala features. And that is a very similar thread executor, which is by default used when you just say site. But that is okay for tests, but certainly not for this application where we need different parallelism requirements. So I put this one reaction, the computation of answer, into its own reaction site that uses the default thread pool. So this will use all cores, as many threads as cores. So on this computer, this will be 4 cores. And all other reactions are in the other reaction site, which has a custom pool. So in this syntax, I declare that this reaction site should use this custom pool, which is declared as a fixed pool with 2 threads. So fixed means that there's always 2 threads in it. So there's another pool called, what's it called? Blocking pool. Yeah, that pool needs to be used if you have blocking calls, and it has a similar functionality to Scala's thread executor with futures, where you do blocking function on a blocking call, and that temporarily increases the parallelism of the pool. But we don't need that here. So this reaction site I already simplified to 3 reactions because I already inlined these 2 function calls into this reaction. And as we have seen by analyzing when these things can run, only 2 of them at most should run in parallel, and so parallelism of 2 is sufficient. Now this pool will have 2 threads that are mostly idle because all they're doing is waiting for the user to enter things or printing things, which is very fast. So these computations are never going to clog the CPU, and it's okay to run them in parallel. So I don't need to decrease the number of threads here. I'll have 4 threads running, performing the computation, and 2 additional threads that are mostly idle. So that's my plan for distributing parallelism among reactions. So this is an example where I have to think about the parallelism, and I think about it in terms of how many reactions do I want to run at once, and should I split things into separate reaction sites or not. So splitting into separate reaction sites is always possible as long as reactions don't compete on the same molecules, don't contend on input. So these 2 reactions have the same input, can show. And actually, I probably should add can show here as well. Because I want to print the final message that the game is over, but I shouldn't be doing this while the user is entering another question. So if the user decides to enter another question at the very end, fine, let's wait until the user is finished, and then we can say that the game is over. So now all 3 reactions contend on this molecule, can show, and therefore they must be in a single reaction site. But this reaction does not have any common input molecules with these, and so it can be in a separate reaction site. So in general, it is better to have reaction sites as granular and as small as possible. For one reason, that each reaction site has its own scheduler, and the schedulers run in parallel. So scheduling reactions here and scheduling reactions here runs in parallel. So if for some reason this is very busy, or the scheduling itself is very slow, which can happen in certain bad cases, this will not affect scheduling here. So this reaction site actually works on user interface, so to speak, in this game. And usually user interface threads must be high priority, so they must not become busy or starved. And that's what we do here by giving them a separate thread pool. Another change in the code is that initially we need to emit these molecules, can ask and can show. I have inlined this code here. So previously my initial code said I'm initially idle, so I'm emitting the idle molecule. But now I eliminated the idle molecule. And instead I need to start this reaction to ask the first question right away. And for that I need can ask and can show. So I emit can ask and can show. So let me run this to see that we have fixed the bug. So right away I can ask a question, and let me ask many questions. 1, 2, 3, 4, 5. So my UI seems to be working very well. I can ask as many questions as I want, and all these answers come, and I can see what happens here. Okay, I'm below 50. Let me do 35. Let me do 27. I'm between 25 and 50, so let me see what I can do. See, I don't get a lot of answers about 36 right now because I only have 4 cores. All right, so I'm below, I'm above 25. Let me try 31. Let me try 45. Oh, I'm below 27 actually. Let me try 22. Let me try 26. Let me try 29. So I'm above 25 and I am below 27. So what can I be? 27. Most likely. So if I start typing a question, then there should be no interference with no answers should arrive. Let me check that this is so. I'm going to type 23, take my time. Okay, no answers arrive. Boom. 27. I'm not greater than 27. I'm not greater than 26. Or maybe I'm below 25. I'm actually below 22. Okay, I'm misguided. 17, 20. I'm below 22, and I am, let me try 10. Oh. What happened? Trying to enter a lot of tries so that I certainly get an answer. Okay, I got an answer. There's one glitch here. I'm not sure what happened. I couldn't make it break, but I was scrolling up and down. Maybe IntelliJ screwed up here. All right, but in any case, we fixed the bug that was there, and we fixed it by adding an extra thread pool and splitting a reaction site into 2 reaction sites by reasoning about which reactions we want to run in parallel and which we do not want to run in parallel. So these are the considerations that a chemical machine forces you to confront. I'm still not reasoning about individual processes in time, but I have to reason about how many of these I want to run in parallel and how many copies need to run in parallel. So all the reactions that contend on the same input molecule, which means their input molecules contain the same input molecule, like in this example, can show all these reactions must be within one reaction site. And this is because this molecule, when emitted, will go to the reaction site and will be stored in the internal storage at that site. And the reaction declared at a different reaction site would not have any access to that storage. So if I actually try to do that, if I try to declare a different reaction site with this reaction, then my code will not compile. It will, actually no, it will compile, it will not run. There will be an error early at runtime. There it is. Exception, molecule already bound. Molecule cannot be used as input in this reaction site, since it is already bound to another reaction site with these reactions. So now I can see what reaction site it means. So this reaction site, that's where CanShow is bound. And this other reaction site I was trying to use it for, CanShow game over and wait for game over. And that's where I tried to use it, but now I can't because CanShow is already bound to that reaction site. So this is the terminology I use. A molecule is bound to a reaction site, which means that it's bound to go there when emitted and stay there until consumed by a reaction. Also notice that the order in which this message is given is not the same as the order in which I declare reactions here. This is alphabetical order, and this is my arbitrary order, but actually the order of molecules is completely irrelevant. It does not have any effect on the execution of the program. So let me undo my change. So that I have a working code. So this concludes this second part of the tutorial. I encourage you to try implementing this game using your favorite framework. You can use actors or just plain Scala with threads or futures or whatever you will. And you will find it's not so easy to make sure that this works. And changes to functionality are not easy to make. And you will find that the chemical machine code is much more declarative. It's much easier to reason about. This concludes the tutorial.